Lecture 54, Gauss divergence theorem and Green theorem. In that lecture, we discussed these two theorems, Gauss divergence and Green theorem. Now, the next theorem, that is in Gauss divergence theorem. So, the Gauss divergence theorem is a relation between the surface and the volume integral. If suppose vector f is a vector point function having continuous first order partial derivative, in the region we say V, which is bounded by the closed surface. So that's in if we say that's in the V, the region V, and which is bounded by the surface, that's in, suppose that's in S1 surface, and this one, the outer surface, is S1. So the double integral f dot nds is equal to triple integration of del f dot dv, that's in divergence of f dv. Here the n, vector n, is an outward unit normal vector on the surface. That's the unit normal surface, the unit normal vector on the surface. So here, that is, we can say the volume integral of the divergence of the vector point function f taken over the volume V, which is enclosed by the surface S. Here that we have two surfaces, S1, S2, is equal to the surface integral to the normal component of f taken over the closed surface S. So you have to remember that double integral f dot nds is equal to the triple integration or the volume integral divergence of f dv. Example, evaluate the double integral r dot nds where S is a closed surface and the vector function r, that is xi plus yj plus zk. Now, as we know, by the Gauss divergence theorem, the surface integral, here we have a vector r n cap ds, that's a surface integral, is equal to triple integral, that's the volume integral, divergence of that vector r dv. Now here r is what? Xi plus yj zk. So first we find the divergence of r vector, del dot r, I del upon del x, j del upon del y, k del upon del z, xi yj zk. Now if we take I dot I, we get 1. The partial derivative of that is 1. So 1 plus 1 plus 1, we get 3. Now from first we can say that S r dot n ds is equal to the volume, and the value of divergence r is 3 dv, that is 3 and dot dv. So what is that? That's in volume, so we get 3v. Here v is what? Is a volume enclosed by the surface, that is S. Next example, find the double integral f dot nds where f is a vector function 2x plus 3z I minus x y z plus yj plus y square plus 2zk, and S is the surface of a sphere having the center 3 minus 1 2 and the radius is 3. Now as we know, first let us suppose, let capital P be the volume enclosed by the surface S. So as we know, by the Gauss divergence theorem says what? The surface integral f dot n ds is equal to the triple integral v divergence of f dot dv. Now we find the divergence of f. So divergence of vector function f L dot f. So we get the partial derivative of that function, that with respect to x. So we get del upon del x of 2x plus 3z del upon del y of xz plus y, this is a negative sign, plus del upon del z y square plus 2z. Now take the derivative here. So we get 2 minus 1 plus 2. So we get 3. So from first we write the value of that triple integral divergence of f dot dv, triple integral 3 dv, and as we know 3, and this is what, this is the volume, so we write 3v. Now here v is what, v is the volume which is enclosed by the surface, and here the surface is what, here v is the volume of a sphere of radius what, 3, and whose center is 3 minus 1 and 2. So as we know, the volume of the sphere which is covered by the surface is what, is 4 by 3 pi r cube, and here r is what, 3. So we get 4 by 3 pi 3 cube, it means we get 36 pi. So 36 pi is the volume. So the value of that integral is what, 3 into 36 pi, that is 108 pi. So the value of that integral we get 108 pi. The value of that surface integral by the help of divergence theorem we obtain 108 pi. So in that way we can use the Gauss divergence theorem. Next example, evaluate the double integral f dot n ds. Or say the surface integral where S is a closed surface which is bounded by a plane z equal to 0 and z equal to 1, and a cylinder that is x square plus y square is equal to 4. And if we have given a vector function f xi minus yj plus z square minus 1 k. So here we are using the Gauss divergence theorem evaluating that integral. So first we have to find the divergence of that function. So the divergence of vector f, that is del of vector f. So what we get, the partial derivative of that with respect to x, 1, that's minus 1, and this we get 2z. So 1 minus 1 and plus 2z. So we get 2z. That's the divergence of f. Now by the Gauss divergence theorem, Gauss divergence theorem, that integral f dot n ds, right, the triple integral volume, this is what divergence of f dot dv. Now this is what, this is 2z dv. Now here we take the limit of that bounded region. So region is what, z is varies from 0 to 1. If you remember the order of integration, so here we see the z is vary from 0 to 1. So we write 0 to 1, that's the limit of z. So now, and the shape, the curved surface is what, is cylindrical surface. So here you can take the limit of x in terms of y and the limit of y is constant, or you can take the limit of y in terms of x and the limit of x is constant. It's your choice which order you are following. So we take the limit of x in terms of y, so we take the limit of y is constant. So here y varies from, if we put x equal to 0, so y varies from minus 2 to 2 if we put here x equal to 0. So that's the limit of y, that's 2. And the limit of x is what? 4 minus y square under root. So minus root 4 minus y square up to 4 minus y square 2z, and on the place of dv we write dx dy dz. Now you just take the integration first with respect to x, then y, and then z. First we take the integration with respect to x. So 0 to 1 minus 2 to 2, and 2z is constant when we take the integration with respect to x. So we write 2z and x and put the limit. So we get root 4 minus y square plus root 4 minus y square dy dz. So this becomes 2 times. So we write 4 times z root 4 minus y square. 0 to 1 minus 2 to 2, 4 z root 4 minus y square. Now take the integration with respect to y. So here when we take the integration with respect to, you can also put the limit 0 to 2 and write the 2 by the property of integral. Now apply the integration. So 2 0 to 1, and the integration of root 4 minus y square with respect to y is what? Is 4z is constant. So we write 4z y by 2 4 minus y square plus 2 sine inverse y upon 2. Apply the limit 0 to 2. When you apply the limit on 0 to 2, so we get 2 integration 0 to 1. You apply the limit 0 to 2 here. So when you apply the upper limit to 2, that becomes 0, and we get sine inverse 1, that says that's become 8 pi by 2, and z dz, that is 2, and that's z. Now that's become cut out 8 0 to 1, 8 pi is constant, 0 to 1 z dz. Now when we take the integration with respect to z here, so we write 8 pi z square by 2, 0 to 1, and finally we get 4 pi. So in that way we can evaluate that integral by using Gauss divergence theorem. Now the Green theorem, the statement of Green theorem, suppose we have in two functions phi and psi are two scalar point functions such that they and their derivative in any direction are uniform and continuous in certain region, suppose V, which is bounded by a closed surface S. So here the volume integral is equal to phi del square phi minus psi del square phi dv. So here is equal to the surface integral phi del square psi minus psi del square phi and ds. So here you have to remember that if C is a regular closed curve in suppose xy plane and S be the region bounded by that curve C, then the line integral m dx plus n dy is equal to double integral or say surface integral the partial derivative of that n with respect to x plus partial derivative of that m with respect to y dx dy. Here that m or n are the continuous differentiable function inside the C. So please remember that statement that's in the Green theorem statement. For example, using the Green theorem to evaluate that line integral x square y dx plus x square dy, where that C is the boundary described counterclockwise of a triangle with vertices 0 0, 1 0 and 1 1. So here we are applying the Green theorem. So as you know the statement of Green theorem, line integral m dx plus n dy is equal to the surface integral, say double integral del m upon del del n upon del x minus del m upon del y dx dy. Now if you compare that with the given integral, so the value of m is what? M is get x square y and n is x square. Now take the partial derivative of m with respect to y, so we get x square, and the partial derivative of n with respect to x, we get 2x. Now apply here, so we get 2x minus x square dx dy. Now first we plot that region. So here we have given a triangle whose vertices are 0 0 and somewhere we say 1 0 and 1 1. That is, we say suppose this is 1 1. If this is x and that is y, so a triangle which is formed by that lines. So here, that is, we can say this is the equation y is equal to x. So now if we take the limit of order of integration, so we take a strip parallel to the y-axis, so we can say x varies 0 to 1 and y varies 0 to that line. So the limit of x is 0 to 1 and the limit of y is 0 to x. That's the limit of y and that's the limit of x. 2x minus x square dy and dx. First we take the derivative with respect to y, then x. On taking the integration, we are taking the integration here first with respect to y, then x. So we get 2x y 0 to x dx. Now 0 to 1, 2x minus x square, thus we get x dx. Then 0 to 1, 2x square minus x cube dx. On taking the integration with respect to x, we get 2x cube by 3 x 4 by 4, limit 0 to 1. On applying the limit, we get 2 by 3 minus 1 by 4, that is, we get 5 by 12. So in that way, we use the Green Theorem to evaluate that integral. Here we convert the line integral by the help of surface integral. Example, apply the Green Theorem to evaluate that integral, the line integral 2x square minus y square dx plus x square y square dy, where C is the boundary of the area enclosed by the x-axis and the upper half of the circle x square plus y square equal to a square. So here if you see the integral, that is line integral C 2x square minus y square dx x square plus y square dy. So here if you may apply the Green Theorem, so that is what? That is, we say m, this is we say n. So now by applying the Green Theorem, we write that double integral del n upon del x means the partial derivative of n with respect to x minus partial derivative of m with respect to y. Please remember, m is what? M is a coefficient of dx and n is coefficient of, that is, say, dy. So we write dx dy. So here that is surface. Now first we evaluate the partial derivative of n with respect to x. So we get 2x. The partial derivative of m with respect to y, that would be 2y minus 2y. Now write s, that is 2x, and we get negative sign, and minus, we write 2 plus 2y dx dy. Now apply the limit. If you see the region here, we have given the x-axis, that's in say x-axis, and the upper half of the circle. So if we draw a circle, so that's y-axis. So here we can say, and that's in upper half. So here x varies a to minus a, and y varies from 0 to that surface. So here that is what root a square minus x square, because we are taking the upper half, or we can say in the upper part of the x-axis. The limit of x varies from minus a to a, and y varies from 0 to a square minus x square, and that is 2x plus y dy and dx. The order of integration, first we take the derivative with respect to y, then x. So we take the derivative, so we obtain the, so on taking the integration, after simplify that integral first with respect to y and then x, you get a result 4 by 3 a cube. So that way we apply the Green's theorem.